So our next speaker is, let me share the screen. So our next speaker is Mr. Hurmal Saren, and Hurmal Saren is currently working as a part-time PhD student at IIT Delhi on a project based on skyrmion in magnetic thin films. He has expertise on electronic and magnetotransport measurements. He also has some teaching experience also. So let's, so yeah, Hurmal, please go ahead with your slides.
Yes. So am I audible?
Yes.
Okay, okay.
Yeah, you can open your presentation. Yeah.
Can I see my slide?
Yes. No, I cannot see your slide, but you need to open your presentation. Yeah, now I can see. Yes. Yeah, please go ahead. Yeah.
Okay. So good to see a lot of my seniors. So I am Hurmal Saren. So I'll be talking about the effect of skyrmion phases in magnetotransport behavior of platinum cobalt aluminum based multilayer thin film sample. So I'd like to mention that this is a collaborative work with Professor Vincent Ross, CNR studies. So in this talk, I will first briefly introduce you to so I'm trying to minimize this video. Okay. I'll briefly introduce you to the skyrmion and the motivation behind our work. Then I'll talk about the sample details and magnetic characterization. And finally, I'll mainly talk about the electron transport measurement, which is basically Hall, magnetoresistance, resistance, and noise measurement. So I'll mainly emphasize on these things. So, okay. So there is some lacking. So magnetic skyrmion, I think most of my previous speaker has already told. So this is a vortex like swirling spin configuration in which the skyrmions can be characterized by the skyrmion number. So there are different kind of skyrmions. This is block wall type, Neil wall type, and then there are different kind of mechanism which can be responsible for this skyrmion formation. And out of this, I would like to mention one, that the competition between the exchange interaction and DM interaction. So exchange interactions basically favors collinear spin arrangement, and while DM interaction, GLSS-Moore interaction favors rotating spin arrangement with 90-degree turn angle. So when there is trade between these two, some spin spiral is formed, and upon applying the magnetic field, we can get skyrmion. So initially, skyrmion were observed in very low temperature and certain magnetic field range, but with the advancement of technology, we can now see the skyrmion even at room temperature. So the skyrmion can be stabilized in the multilayer structure of this heavy metal thin film, where this DMI, Jealousy-Moore interaction, arises from the interfaces and the spin orbit coupling due to the heavy metals. So because of the additive nature of this DMI, which aids the formation of skyrmion at room temperature, we can observe it. Okay, so uh, uh, this has huge potential in spintronic device application. So when we apply some electric current to the skyrmion, so this skyrmion can be moved by spin transfer torque, and because of this emergent magnetic field, because of this skyrmion spin texture, this electron can be detected, and this can give rise to the topological Hall effect in this transport measurement. And there is also some skyrmion Hall effect also, in which the skyrmion not only moves in the straight line, but it has some component perpendicular to the straight line. So this is the transport measurement on MNCI sample. So if pointer, let me select pointer option. Okay, so this is the Hall measurement data at the skyrmion phases. So field is constant, and they have done the measurement at different temperature. So you can see at the raw data also some kind of harm kind of structure. So upon subtracting this anomalous and ordinary Hall component, you can get some harm kind of, which amplitude is very small. So these are the topological Hall effect. So so because of this small size, less than 100 or so, and extreme stability and low deepening threshold current, it has huge potential in spintronic based device application. And for that, one needs to understand this charge carrier transport. And this is our motivation to understand this charge carrier transport behavior. So, okay. So this is the sample details. We have got it from the CNRS college. So this is basically a trilayer structure of platinum, aluminum, cobalt, which has high repetition. And this is the fabricated device using optical lithography. And this contacts are made by uh, 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 gold wire bonding. So we have done most of the measurement on this kind of sample geometry. So I would like, before going to the transport measurement, I would like to show this global and local magnetic behavior. So this is the squid measurement. This is saturating at 190 milliliters, and you can see between that you can see some kind of uh, some kind of trend, right? So at what field, what is happening for that? This magnetic field dependent MFM is done. So starting from the zero field during the upsweep, you can see some one kind of structure. So upon applying the magnetic field, so this is out plane magnetic field, right? So upon applying the magnetic field of around plus 80 milliliters, so we can see some kind of round structures. So these are basically skyrmion and some kind of elemental structure. So these are kind of the mixed phase. So upon applying the magnetic field further, so at around 95 millitesla, we can see this perfect skyrmion, and this density is high. And when the magnetic field is increased above that at around 145 millitesla, you can see this density is density of the skyrmion is reduced, and uh, uh, the size is also reduced, it seems. So if we do the transport measurement, what we're expecting. So to do that, we have done the Hall and magnet resistance measurement. So this magnet resistance measurement is also in presence of out of plane magnetic field. So this is the Hall measurement data. This is I have made it symmetric to extra the extra Hall component. So you can see this exactly follows this magnetization curve, and this is the tip. Uh, resistivity data, longitudinal resistivity data. So if you see closely, suppose this red curve, this upshift data, you can see around that point, you can see the change of the slope. And even for the blue curve, if you see, you can see slight change of the slope. So I have analyzed it later, so I'll show you. So from this Hall resistivity data, I have tried to extract the extra Hall component if there is any. So I have calculated this ordinary and anomalous component, this red one, and I have subtracted it from the total Hall component data. So what I got, that we can see peak and dip at certain field at around plus minus 124 millitesla. We see dip, and the positive side at around that field, we can see peaks. So if you see the range, this is in the nano ohm centimeter unit resistivity range. This is around 80-90 nano ohm centimeter. So in the literature, this kind of extra Hall resistivity is termed as topological Hall resistivity, and as our data is also showing a similar time to us, we can say that this is kind of topological Hall resistivity data, and this is quite established. So apart from that, what I observed interesting. So just track this red data. So you can see beyond that circuit, you can see this harm kind of structure. So this seems to be a weak region. So in the downside data, you can see at the left side, so you can see some harm kind of structure. So we don't know the origin where is it coming from. So this is coming all the time. So we have done this measurement 10 times and taken the averages, and from that I have tried to calculate it, and this is coming always. So okay, so to find the origin where this extra Hall resistivity or topological Hall resistivity is coming, I have tried to plot it with the skyrmion number, which it from the magnetic field dependent data that has been calculated. And if you see that when just first see the left side, when there is no skyrmion, the skyrmion number is 0. You can see some flat, flat extra Hall resistivity data. So while the skyrmion is developing at around this field, you can also see this feature peak in the left side, and similarly in the right side also at around where the skyrmion density is maximum, we are getting peak in the extra Hall resistivity or topological Hall resistivity. So we can kind of correlate these things. But this low weak feature, this weak feature harm kind of structure, we can't say anything because it showing some trend, but this is not which I mean we're not able to correlate with the skyrmion number. Okay. So this is the magnetoresistance data in out of plane magnetic field, I mentioned, and how it is correlated with the Hall data. So as I was mentioning, I mentioned in the previous slide, this we can see some change in the slope. So to visualize it, we have taken the first derivative and plotted in the same plot. So at around this field where the slope is changing, you can see this peak deep. I mean, and in the positive side also we can see some kind of peak. And interestingly, if you see closely, when I compared with the Hall resistivity data, this this position of this peak or dip is almost same. And interestingly, this slope feature, which we observed in the extra topological Hall resistivity data, this is also present in this. But this is this was I think DC measurement, so this is not that clear, but it is still present. We have done the AC measurement, and this weak feature is also present. So this origin of this weak feature is still not clear to us. So later, now we have done the noise spectroscopy measurement, but before that, I'll like to introduce you briefly to the noise spectroscopy. So what we do, so basically we take the time series voltage data. Time series voltage data. So if this voltage signal is totally random, this is the time series data. If this voltage signal is poorly correlated, so this is what time domain signal looks like. And if this signal is intermediate, that means not that random or not that smooth, this is what it look like. So from from this time series data, by using Fourier transformation, we do this frequency domain data, and upon squaring this average value of frequency domain data, we get the noise power spectral density. So this is for this is the plot of power spectral density with the frequency. So we basically observe how much power is associated with different parts of frequency spectrum. So if this signal is purely random, you can see some white noise. So this is kind of flat. If the signal is poorly correlated, we can see 1 by f squared type. And if this is intermediate, signal is intermediate, we can see 1 by f type, 1 by f to the power alpha, where alpha value can vary in between. Right. So in our measurement, this is done using the lock-in amplifier and the spectrum analyzer. So we have done this measurement using that tool. So left side, this is the voltage per spectral density with the frequency with different magnetic fields. So I have calculated this voltage per spectral density at 1 Hz and plotted with the magnetic field. So you can see that at around 74 millitesla plus 74 millitesla and plus 100 millitesla, we can see sharp peak. and above that we see, but this is not that strong. And I would like to mention that the field protocol, what we have used in MFM and what we are using in the noise measurement is same. So to investigate this pattern, why we are getting, we have plotted with the skyrmion number. So if you see this red one is skyrmion number, blue one is the noise. If you see that uh, it seems that the noise is uh, becoming maximum at around the skyrmion phases, this 100 millitesla one. But at 70 more millitesla, there might be some mixed state of skyrmions and this elongated structure. So we might get this feature because of that. But we are not sure about that. So again, to correlate with the extra Hall component, to correlate with the extra Hall component, what we plotted that at this field, this extra Hall topological Hall will become maximum. And before that, before reaching to that point, so we are getting this noise peak. So basically, skyrmion, basically this noise is becoming maximum at before the skyrmion, high density skyrmion phases for. Right. Later we have plot try to find this correlation between the alpha value, that is the frequency exponent, that is alpha 1 by f alpha. With the skyrmion number. So if you see that this trend is again that not straightforward. So at high field where there is no skyrmion, you can see some constant at low value of alpha, which means that the charge carriers are becoming faster. So at around this phase, so this around these phases, that means for the skyrmion density is maximum, we can see that the high value of alpha, and that means slower dynamics of charge carriers. Charge carriers. So, in this analysis, we have taken data from the different set of instruments like SQUID, MFM, and this for the transport measurement we have taken. So we are expecting that there might be some field mismatch. And to investigate that, we have tilted the sample with respect to the z-axis and done the transport measurement. So this is the topological Hall resistivity calculated for the 5-degree tilt data, plotted with the skyrmion number and the noise. So if you see that this skyrmion number, this peak of the topological Hall resistivity is matching, and this noise is becoming maximum before the skyrmion phases, but the carriers are might be facing a lot of fluctuation, right? And at the high field, we can see there is no variation of the noise, so there is no variation of noise. So this tells us that this phenomena, what we are observing in the transport measurement, electronic transport measurement, might be correlated to each other. So if I summarize that we observed subtopological Hall-like signature. This is very strong and robust. This doesn't depend with the variation of the resistivity, longitudinal resistivity. We have also observed this peak in the MR data, also first derivative of the MR data also. We have observed this hump-like peak feature in both Hall and MR data. And we have observed this electronic fluctuation around high density skyrmion pages. And we have observed certain variation of alpha, which indicates how fast or how slow the carrier dynamics is. So that's it. I'd like to thank my supervisor, Professor Pintodas, and our collaborator, Professor Vincent Cross, and Yogesh Kumar, Fernando Ajijas, Nicholas Reren, for their support. Thank you.
Yeah, thank you, Hurmal, for your nice talk. So do we have some questions for the speaker? Okay, so if there is no question, then we can move to our
question
next.
from Dilip Gupta.
Okay. Sorry, sorry. Yeah. Please, Dilip Gupta ji, please.
Yeah, Harman, when you have measured transport in the vertical direction, why is this is going down at the zero? Means at the higher field it is the maximum, and at the zero field it is minimum. So it seems it's inverted.
This one?
Yeah. All of these kind of plots means this is all going down at the zero, and then.
Okay, so this is because this Hall effect is due to electrons, so negative charge. That's why we're getting like this.
No, even in the normal transport, magnetoresistance you have also measured, na? No.
Okay. Even this one?
No, slide has not changed. This is the Hall effect, right?
Can you see my slide?
Yes.
Okay.
Yeah.
So can you repeat the question? Sorry.
So my point is, in the magnetoresistance you have measured transport.
Okay.
Is the Hall transport or normal magnetoresistance, anisotropic magnetoresistance, vertical direction?
Not the anisotropic magnetoresistance. This is the magnetoresistance in outer plane field.
So magnetoresistance is here is anisotropic magnetoresistance, right? Because it is not giant magnetoresistance or tunneling magnetoresistance, so it's an anisotropic magnetoresistance, right? So my point is, in magnetoresistance, why this is going downward at the lower field, and the at higher field it is maximum. So it seems it's inverted. Normally, magnetoresistance in let's say GMR and T1, it's going up direction.
Dilip ji, if I may add a comment, I think these multilayers have a positive magnetoresistance. So you have lower resistance state at zero field and increasing resistance as you go up.
Okay.
Yeah, most of these multilayers have that behavior.
Okay. Thank you.
But then it might also reverse the sign, depending on what normal Hall coefficient you have.
Okay. Okay, fine. Thank you.
Yeah, I have a related question to this plot on the right side. So on the negative field, there is a gap between these two red and blue data, right? It is not there on the positive field.
Yes, sir. So this change in this resistivity is very small. So this even the voltage change was quite small. So we're saying that this might come from the electronic drift of the instrument.
Okay. Yeah. So do we have more questions, or otherwise we can? At least I cannot see anyone raising hand. So